of a graph. So a factor of a graph is basically a spanning subgraph. And if the spanning subgraph is a regular graph, then we say it's a k factor if the regularity is k, all the vertices have degree k. So a k factor is basically a k regular spanning subgraph. And a one factor therefore is basically a perfect matching because it must be spanning and every vertex must have degree 1 in the subgraph. So only a matching, perfect matching will have this property. So basically a one factor is a perfect matching, two factor is basically a collection of cycles, and similarly you can go to other higher degrees. So here is a graph, example graph, where you see that you have a one factor like maybe this, right? So this is basically a one factor. It's a perfect matching which saturates all the vertices. Then I can define two factors. Look at this. So maybe I will see. Let's take these edges, and I get a big cycle which goes through all the vertices, and therefore it's a two regular subgraph, right? I take only those edges, then I will get a two regular subgraph, and that is a two factor. We can have other two regular subgraphs here. For example, I can just pick this four cycle here and this cycle here, right? So these two cycles, disjoint cycles, they also form a two spanning subgraph, which is also two regular. So that's also a two factor. Now, what we want to ask now is that when does a graph have a perfect matching or a one factor? So because in the Hall theorem, we are looking at bipartite graphs only, right? Now one can ask, okay, for general graphs, what can you say about the existence of one factors or two factors? But we are going to look at the case of perfect matchings at the moment. So when can we say that a graph has a perfect matching, an arbitrary graph? So like again, we can see some necessary conditions. For example, if you take any subset of the vertices, okay? So take the graph that we want and take any subset of the vertices, let us say S, and I remove these vertices from the graph. So you take any arbitrary subset, remove that vertices from the graph, you get a graph which is on the vertex at G minus S. Now this graph, let us say that it has several components, and some of the components have even order and some of the components have odd order. Now if there is an odd component, then we know that odd component cannot have a perfect matching because the odd so every matching basically pairs vertices, and and if there is odd number of vertices in a component, of course we won't be able to pair one of the vertices definitely. So now how do you pair this vertex? Of course it can only be paired if that vertex or some vertex has a neighbor outside, right? And where can this neighbor be? It can only be in S because like the entire graph is joined by S if it is connected to begin with, is joined by S, and that is the only way possible, right? So which means for every odd component you should have at least one neighbor in S, and these all should be distinct neighbors, right? Because to define a matching we need to have these edges all disjoint. So which says that if you look at the number of odd components in G minus S, it cannot be more than the number of elements in S itself, right? So the number of odd components, let me denote by let's say of G minus S, right? This must be less than or equal to the cardinality of S, right? Because corresponding to each odd component, we should have some vertex in S. And this is true for any arbitrary subset S of the vertex set of the graph G. So this says that this is a necessary condition, right? Because if this is not true, of course we cannot have a perfect matching. Now the question is that, is this condition also sufficient? And it was proved by William Tutte, that indeed this necessary condition is also sufficient, which is quite surprising. And that is called the Tutte's one-factor theorem. Okay? So for every subset of the vertices, the number of odd components in G minus S is at most the cardinality of S. If the graph has a one-factor, and Tutte's one-factor theorem says that a graph G has a one-factor or perfect matching if and only if the number of odd components in G minus S is less than or equal to S for every subset of the vertex. Let us denote this condition by star, right? This inequality for every subset. That is the property which is called which is denoted by star. So now we want to prove this. Again, the only if part, which is the necessary condition, is trivial, right? So because if there is a one factor, we know that this property must be true, and or if this property is true implies there is a one factor is what we need to prove. That is the if condition. So how do you prove the sufficiency? Okay. So we are going to use induction on the order of the graph. Right. So you might have already seen that induction is quite powerful tool, especially when we are dealing with the properties of graphs. In many examples, you might have already seen it. We are yet again going to use induction here. We are going to use induction on the order of the graph, and the starting case we will say that if the order of graph is 0, right, there is nothing to prove, right? This is clear. Now let us assume that the graph has non-zero vertices, strictly greater than 0, and the result holds for graphs of order strictly less than order of G, right? For all the graphs with order strictly less than this, then the result is true. That is like if for that graph, all the subsets of this property implies there is a perfect match. That is true. Now to develop our proof, we will assume that so we might have several subsets where this, of course, for every subset the inequality is true, but for some subsets the inequality might be also equality, right? That is possible. So we define S0 to be a maximal subset of the vertex set such that the equality holds for the condition star that we define, right? That q of G minus S0 is equal to cardinality of S0, right? So we will assume that equality holds and S0 is maximal in the sense that we won't be able to add any more vertices to S0 and still have this property that q of G minus S0 union something is actually equal to the cardinality of S0 union that something. Okay, so we will define S0 to be a maximal subset with this property where the equality holds. Okay, so here is a picture. So let us start by the assumption that suppose S0 is the empty set itself, right? Because we are looking at the maximal case, and then maybe there is no maximal non-empty set. So S0 is empty set. So what if S0 is the empty set, right? If S0 is empty, then, if you remove the empty set of vertices, then you have several components of the graph. Of course, all of them must be even components, right? Because if one of the components of the graph is an odd component, there is no perfect matching, we know. And we know that because the condition star holds for every subset, for this also it must be true. So therefore, all the components must be even, right? But now let us pick one of these components. Let's take any of the components. Each of the components even to ck are all even, right? Pick one of them and just remove some arbitrary vertex from this, right? So take the ck, right, or ct, whatever, and then just remove some arbitrary vertex from this. Now, if I remove one vertex, what happens to this component? Well, this component, you have removed exactly one vertex, right? Then the remaining number of vertices is odd, right? The entire component, right? Because we started with an even component. And because it is odd, we should definitely have at least one of the components which is odd, right? Because if there is no odd component, the total vertices in the components will be even. So we know that there is going to be some odd component in ck minus x. But because we know that every subset satisfies the property, right? We know that there is at least there is at most one component, right? Because we have only one vertex that we have removed, and therefore the number of components cannot be more than one also, right? So therefore we have exactly one component in ck minus x. But now let us just add this x to our S0, which is the empty set, right? So if you take the entire graph and remove x from this graph, right, then what happens? Again, x had the several components, and one of the components was this ck, and we have removed this x, and for this we know that there is precisely one odd component in the remaining graph. But that says that our S0 was not maximal because we have just added one vertex which is x to S0. We got a non-empty set, and we also show that the condition star holds with equality, right? Because we have exactly one component, we have exactly one vertex in S. So therefore, S0 as empty set is not maximal. So we can now assume that our maximal set is a non-empty set, right? S0 is non-empty. So again, to just recap what we mentioned, right? S0 is empty, then D consists of even components by the property star. But then if you pick any single vertex, right, the remaining graph after removing this has at least one odd component because the number of vertices remaining is odd in that component. But of course, by the property star, it has at most one odd component, and therefore it has exactly one odd component, and therefore S0 is not maximal. Okay. So we continue with the assumption that S0 is non-empty, right? And take such a maximal S0 and G minus S0 I'm going to look at, right? So if you look at G minus S0, it will have some components C1, C2, etc. Let's say CEM, where C1 to CM are all odd components, and then some more components D1, D2, etc. Let's say DK, which are even components. But we know that the number of such components M is actually equal to cardinality of S0 because we have said that S0 is the one which is maximal with the property that the number of odd components is actually equal to the cardinality of S0, right? So therefore, this M is strictly greater than 0 or is at least 1, right? So we have at least one component, right? One odd component, and there are exactly S0, which is M, many components C1 to Cm. Now, so what do we have here? So we have we have S0 has to be a maximal subset with this property, and our aim is to somehow use this to come up with a perfect matching, right? So we want to somehow construct a perfect matching. So the idea is that we should be able to somehow figure out vertices in the components to be matched with the elements in S0 to come up with a perfect matching. And how do we do that? We first show that if I take one of these components, any of these components, let's say Ci, right, and remove one vertex, okay? So take any component, any of the odd components, and remove one vertex, any arbitrary vertex. We show that this graph must have a perfect matching. Okay? So we are going to show that any of these odd components in this situation, right, G minus S0, if G minus S0 is in fact S0 is maximal and G minus S0 has the property, right, equality is true for Q of G minus S0 equal to cardinality of S0. Then we show that if you pick any of the CIs and remove any vertex from that, then the remaining graph Ci minus that vertex has a perfect matching. And since we can choose this particular vertex, we will use that vertices, right, which has neighbors in S0 to come up with our perfect matching later. Okay, so that is the idea. So we are going to do this. So let us say S0 is non-empty, and then this we already stated. Now what I want you to think about is that the even components di, right, d1, d2, etc., dk, we said they satisfy star, so they all satisfy star. I mean, and I want you to think about this for a few seconds. Why, right? So each di satisfies star. They are subgraphs, even subgraphs of G minus S0, and each of these even subgraphs satisfy star. That is the claim. Okay. So essentially, if so di is an even subgraph, we know that the graph G, right, satisfies the property star, right? But then when you look at G minus S0, we know that S0 satisfies this this inequality where it attains equality also, right? Because it attains equality, you can show that, like, if you take any arbitrary subset, right, of this D1, right, we can basically put that to S0, right, and still the equality must hold true, and therefore that will imply that DIs, each of them must also satisfy the equality star. I mean the inequality star. Okay. So because the property holds by the choice of S0, and star holds for the entire G, right? Any arbitrary subset of vertices in G, one can show that each di satisfies this. And since di is an even graph with strictly smaller order, right? We, by induction hypothesis, each of them has a one factor. So we don't have to worry about the even factors, right? They all have one factor by even components, because they have one factors by induction hypothesis. Now, as we mentioned, we are going to pick up some arbitrary component C, right, for any of the odd components Ci, and pick it as and call it C. And we pick some vertex, arbitrary vertex, any vertex from this component, right? And I look at this component Ci, which is called C now, right? And then I just remove this vertex V from this. So I get a graph which is, so the X is, or X or V is sitting outside, right? Having some neighbors. And this is basically C I minus V, which I call C dash. Okay. So each component I can do this. I pick some arbitrary component and do this. Like I remove a vertex, any arbitrary vertex, and I look at the graph C dash. And I am going to show that C dash has a perfect matching. So C dash has a one factor, that is a claim. And how do we prove that? Okay. Suppose it has no one factor. So if C dash has no one factor, then because C dash has strictly smaller cardinality than G, right? You know, if it has no one factor, then the property star must fail for some subset, right? Because if the property star is true for every subset, we know that by induction it has a one factor. Therefore, for some subset of vertices of C dash, the property the star is failing, which means that the odd components in C dash minus S is strictly greater than the cardinality of S for this subset S. Okay. Now, if you look at Q of C dash minus S, right, plus cardinality of S, right? So what is that? Q of the odd numbers in C dash minus S plus the elements in S is actually equal to cardinality of C dash, right? Because that is what we have. But cardinality of C dash is by definition, we started with C I, which was an odd component, removed one vertex. So C dash has exactly even number of vertices. So therefore, this is basically 0 modulo 2, right? It's an even number. That's what we are saying, right? But then, what can you say about Q of C dash minus S? Now, Q of C dash minus S must be at least cardinality of S plus 2, because if S is odd, then we should have Q of C dash minus S should be another odd number. And if S is even, we should have this also to be even, because the sum is even. So therefore, Q of C dash minus S is greater than or equal to cardinality of S plus 2 if the strict inequality here is holding. Right? So if this is strict inequality, then this must be the case. So we are going to use this property now in our proof. So to do this, what we do is that we look at the graph now obtained from G by first removing S0, right? Then removing the vertex V that we chose from the component C, and then the subset that we obtained just now, right, which violated this property for the component C dash, right? So look at these vertices and remove these vertices from the graph, right? Now we know that because for the entire graph G, for every subset, Q of G minus that subset is less than or equal to the cardinality of that subset. And how many elements are there in the subset? We have S0 elements we have removed first. Then we have removed V, which is one vertex, and then we have removed S from CI or C minus V, which is cardinality of S many vertices, right? So because this inequality holds for the entire graph, we have this inequality, right? Now what is this? This is like, so once I remove G, if I look at G minus S0, right? Look at the odd components in G minus S0, out of which we removed one, right? That one, because we removed one vertex from that, Ci, right? So that is Q of G minus S0 minus 1, right? And the remaining is the number of components in Q of C dash minus S. That is by definition, that is the number of odd components that remains, right? Because other components are all accounted for here, and the remaining are even components. But Q of G minus S0 is actually equal to cardinality of S0 by definition of S0, right? Because it is equality attained there. And Q of C dash minus S, we know that is at least cardinality of S plus 2. So that 2 will account for the minus 1. So I get cardinality of S0 plus 1 plus cardinality of S. This is greater than or equal to this. But now this both sides of this Q of G minus S0 union V union S are bounded by the cardinality of S plus 1 plus cardinality of S0. Therefore, it must be equality. But what does this tell, right? If you take this graph, right? So this is what happened here, right? We have taken the graph, we removed S0 first. Then we had several components, C1, C2, etc., Cm, odd components. And we have taken one of the components and removed one vertex, which is become the even component. And then from that even component, right, we have found out that if it is not perfect matching, if there is no perfect matching, we can remove some subset of vertices such that the number of odd components is strictly greater than, right? So we have taken that, and then we are counting the odd components here and the odd components here, right? And that is what we got this, and we show that for this subset, right, I remove first S0, then I remove V, and then I remove S. And after removing this, the graph has exactly this many odd components. So which means that we could add to S0 some other vertices, non-empty set of vertices, for example, 1 plus cardinality of S, whatever it is, right? So some non-empty set of vertices and still have the equality, right? Which contradicts the assumption that S0 was maximal. Right? So therefore, the assumption that we made that there is no perfect matching for C dash minus V, for C minus V is wrong. And for each of the odd components, you can remove any single vertex and the remaining graph must have a perfect match. Okay, so what we have just shown contradicts the maximality of zero, and therefore for each I, and our choice of Ci is were arbitrary, right? We pick any arbitrary vertex, arbitrary component Ci, and we pick any arbitrary vertex in that, and therefore for each of them it must be true, right? Therefore for each I and each vertex in Ci minus V must have a one factor. Now to define the perfect matching for the entire graph, we are going to define a bipartite graph. Okay. So the bipartite graph, H is defined as follows. So you take the odd components C1, C2, etc., Cm as the vertices of one set, which is, let's say, called X, and then the other set I call as Y will be the vertices in S0. Okay. Now, how do we join the edges? So for every vertex in X, which is a component Ci, is joined to those vertices in S0 which has some neighbor in Ci. Okay. So if the neighborhood of Ci contains S0, that at least one of the vertices, each vertex which has some neighbor in Ci, right? We will put them all in the graph. And the graph H. So as edge. So there is an edge from small s in S0 to the component Ci if S belongs to the neighborhood of Ci. That at least one vertex in Ci is adjacent to S. Now we show that this graph has a perfect matching by using Hall's theorem. Okay, so we have just proved Hall's theorem before, right? So to use Hall's theorem, we just need to show that for an arbitrary subset of vertices of X, let us say, its neighborhood, right, must have, so if you look at the neighborhood, then the condition that cardinality of A is less than or equal to the cardinality of the neighborhood must be true. Now, how do you show that? To show this, we use the property star, which is true for the graphs. And I want you to think about this, like cardinality of A, one can show is less than or equal to Q of G minus B, where B is the neighborhood of A in H. Okay, so that the set of vertices in H, right, in the neighborhood of A as B, and which is of course a subset of Y, right? Y is our S0, right? And this first inequality holds, and I want you to think about and tell me why. Okay, so you can write it down when you write down your notes. And then the second inequality is immediate because the property G of Q of G minus B is less than or equal to cardinality of B holds for every B. And therefore, by Hall's theorem, H has a one factor because again, this property is true. It will saturate all the vertices in A, and one can show that the number of vertices in here and there are same because S0 and the cardinality of CAs are the same for our choice of S0. Right? So therefore, any matching which saturates A will also saturate B. And that's it. So we have shown that we have a perfect matching for this. So now what do you do? So you take this perfect matching, which basically matches elements of S0 to some vertices in CI, right? So and each CI has exactly one neighbor, which will be picked for the matching. And then we know that that's CI minus that vertex, any vertex, has a perfect matching by our induction. Right? And then DIs all have perfect matching by our induction. And therefore, altogether, we get a perfect matching for the graph G. So we start with S0, then we have these components C1, C2, etc. Cm, and M is the number of the cardinality of S0 itself, and the perfect matching between S0 and these components fix some vertices right in each of the components, and removing that vertex, Ci minus that vertex has a perfect matching, right? Each of them has a perfect matching. And then we have this matching between these vertices, right? Each of these vertices is saturated now. And then the remaining DIs are even components, and by induction, that also has a one factor. And putting all this together, all the vertices are saturated, so therefore the graph has a perfect matching or one factor. So here are some homework questions for you. So let G be a graph and T be some subset of the vertex set. Okay. Then G has a matching that saturates T if and only if Q of G minus S bar T is less than or equal to cardinality of S for every S subset of V, where we define Q of G bar T is the number of odd components of G whose vertex set is contained in T. Okay, so we have G minus S bar T says that like G minus the number of components of G minus odd components in G minus S that is contained in T. So so basically this is what you want to show. Second question is to prove that a tree T, let us say, has a perfect matching if and only if for every vertex in the tree Q of T minus V is equal to 1. The number of odd components in T minus V is 1. If that is true, then the tree has a perfect matching. And only then. So that question asks you to show that if you have a three regular graph whose edges can be partitioned to perfect matchings, right? Then this contains no cut vertex. Okay? So a three regular graph whose edges can be partitioned to perfect matchings cannot contain a cut vertex. Okay, here is another question. So I have given you a graph and show that first of all, you find maximum matchings in this graph G as well as the graph G plus xy, which is obtained by adding an edge between x and y in this graph. Right? I have marked x and y, and then prove that it has no larger matchings, right? That is actually a maximum matching, right? Okay, so it might be useful to recall some of the results that we proved earlier, connecting matchings with other parameters, etc. Right? What are the other parameters? Matchings will be upper bounded by something, etc. And then show something like that. Okay, I think That is all I have for today's. But if you want, I can basically try to answer some of the. We will start a new topic in the next class. I mean next week. And anything about the earlier assignments or something, I think there were some questions which many students were finding a slight difficulty. For example, one question that a couple of students mentioned to me was that there was this question about minimally two connected graphs, right? And then show that it has vertices of degree 2. Right? So how do you show something like this? Okay? So first of all, so look at this. So if a graph is minimally two connected, then by definition of the graph being minimally two connected, if you remove any edge from this graph, it must not be two connected, right? That is why it is minimally two connected by definition, right? So for every edge, the removal of this edge will result in a graph which is not two connected. So if the graph is not minimally two connected, then you should be able to find some edge whose removal will not remove the two connected property. Now, what does that mean? So if removal of an edge is still keeping the graph two connected, means that these two vertices must be in some cycle, right? That's something that we have already studied, right? If the graph is two connected, any pair of vertices belongs to some cycle, right? So if I remove this edge, you still have some cycle in the graph going through these two vertices. That is why the graph is two connected. So which means that for this cycle, this edge is a chord that we defined what is a chord, right? A chord is an edge which joins two non-consecutive vertices of the cycle, right? So there must be some edge which is a chord, right? So if a graph is two connected and is minimal, then you cannot have such edges in a graph. That no cycle can have a chord. Okay, so two connected graphs without chords will be precisely the minimally two connected graphs. So if you make this breakthrough, then you have to just show that if to show that there is a vertex of degree less than or equal to 2, right? All you have to show is that if the minimum degree is greater than 2, then you will always have a chord, right? Now how do you show that you will always have a chord? So we start with the assumption that a minimum degree is at least 3, right? Now first of all, if you recall that, we can show that if the minimum degree is 2, then it contains a cycle. And what was the argument? One of the easiest argument is to use maximality. Okay, so what you do is that you start from any vertex, and look at not any vertex. You look at a maximum length path in the graph. Okay, so the largest path in the graph, this is P. Okay, so this is the longest path in the graph. And this path, if you look at the starting vertex, of course, its minimum degree is at least 3, which means that there is some neighbor to this. Now, can this neighbor be outside this path? If it is outside the path, then you have a larger path. So therefore, the neighbor must be inside the path, which means that there is some neighbor in this path, and this says this defines a cycle, right? So we have a cycle. But we know that the minimum degree is at least 3 for our graph, so which means that it has another neighbor, right? So some other neighbor. Now, if there is another neighbor, then you just look at the the cycle found by the neighbor which is farthest from the on the path from this vertex x that we started, and look at the cycle that we have defined, and for that cycle, this edge that we have just added now must be a chord, right? So therefore, we already know that uh, if the minimum degree is at least 3, there must be a chord. But if there is a chord, I can just remove this and still maintain the two connectivity between those two vertices. So therefore, we should have vertices of degree at most 2. But now, of course, the degree cannot be less than 2, because then the graph will either be disconnected or it will have pendant vertices which are not going to be 2 connected. So therefore, we know that there must be vertices of degree exactly 2. Okay, so that is how we can prove this. And once you know this, you can prove the second part also. Okay, prove the second part. That second part of the question was asking to show that the number of vertices, if n is at least 4, is 2n minus 4, at most 2n minus 4, right? Now, because you have degree 2 vertices, okay, I will give you just an idea, like degree 2 vertices in the graph that we have. Suppose you take this graph and pick some degree 2 vertex and remove it, right? If I remove this vertex, then you show that if it is either two connected or not, you will have vertex of degree less than or equal to 2. Okay? Because if again the minimum degree cannot be 3, because then in that that subgraph will definitely contain a chord, right? So once I remove this vertex, you will see that the remaining graph must have vertex of degree less than or equal to 2. Then I can pick that vertex, remove that also. Then I will have another subgraph again degree less than or equal to 2. So you see that you can find a sequence of vertices where every time you are basically adding a vertex and only at most 2 edges to it. So you start with you just look at the graphs with exactly 4 vertices and look at all possibilities, and you see that you cannot have more than 4 if the number of vertices is 4. And for n is equal to 4, we know that 2n minus 4 is actually equal to 4, right? 2 into 4 minus 4 is equal to 4. But then once you have this onwards, you can only add, like we know that we have to add vertices of degree at most 2. Every time you introduce a new vertex, if you go in the reverse order, you will add at most 2. And therefore we see that we have n minus 4 into 2 at most that we are going to add, plus 4, which will be 2n minus 4. So at most this many edges we can add. Okay? So this tells you how to approach such questions. Okay. I think I can wind up unless you have any more questions.